Alright, I'm looking at section B there in 2012 is the question I gave you out there, question 6 in the technology exam papers, right? So I'm going to throw that exam paper down here and look at the question. Okay, so the graphic shows a student designed for a light sensing buggy. Okay, the buggy contains the following parts: 3 light sensors, S1, S2, S3, 2 motor driven wheels, 1 and 2, and 1 free turning rear wheel or a caster or whatever there at the back of the thing, and a suitable control circuit there sitting on the back of the buggy. The buggy is designed to move forward or turn towards a light source by running one or more or both motors controlled by the system showing. Okay, so when it's in the front, it goes forwards, the 2 motors are on. When it's on the right, or when the light is shown there on the left hand side, the motor turns and goes towards it, and when it's on the right hand side, the left motor turns on and turns towards the right because of the caster at the back, right? Here we can see, I suppose, what's going on inside in the control circuit, right? So we have 1s and 0s, and we have NAND gate here and NAND gate here, and motor 1 and motor 2. Now for motor 1 and motor 2 to be turned on, you need an output out of the NAND gate of 1. Right? Those outputs need to be 1. Okay, so we need to figure out how we're going to get that done, but that's later on in the question. Okay, when sensor 1 is in darkness, you get a 1. When sensor 1 is in light, so i.e. when the light is on over here, when the light is on, that's when we get a 0. Okay, so we'll just have a look at that there for a second and we'll get back to it. Start with part A. Name a suitable component for use at light or at S. It's a light sensor. So what light sensor are we going to use? I've it written down here. It's an LDR. It's a light dependent resistor. Okay, it has high resistance in darkness and low resistance in the light. Okay, number 2 there, it says what property of this component changes with changing light levels? The answer there is obviously resistance. Okay, so the resistance changes with light levels. I'm going to stop putting the exam papers over and back now because that's going to annoy me. The light sensors will be placed in a potential divider in the circuit. Okay, what is meant by a potential divider? Okay, so I've drawn a diagram, a quick diagram there. So basically voltage in here, going from positive to negative, sort of electricity is going all the way around in this circuit. Okay, so we have resistance 1 and resistance 2 here. When the electricity, the current has to flow through resistance 2, R2. It has to go through here. It has no other option. But it has 2 options then. It can either go this direction, or it can come out here and go to V out, which is our motor or whatever the hell we want to control. But it'll depend on which one of these 2 pose the greatest resistance. So if I was to put a very, very high resistor here, then the electricity has to go in this direction. It has to change its direction and go out and go through the motor and then find its way back to ground or to the negative of the battery. If the resistance of this is turned down, then it won't bother going out through the motor and it'll take the easiest course of resistance going back to ground. So if I had a variable resistor here, or what you might call a dimmer switch for your lights at home, I can turn it up and turn it down and thereby control the amount of electricity or amount of current going through that motor. Right? The reason it's used, or the reason it's required, is so the motors can be individually controlled. Right? So we can send the current one way or send the current another way depending on what we want, right? And that would essentially steer the buggy. Okay, that's the simple part of this question done, lads. Part B. The part B is shown is an incomplete truth table for the buggy control system. Now I sent you notes the other day on that. Hopefully you got to look at them, and you know they made some bit of sense. Right here we're going to explain some of it. I'm going to move my board across there. So shown is the incomplete truth table for the buggy control system. The system uses NAND gates. It's an AND gate followed by a NOT gate. So if you were looking at the notes, you would know, you'd see what those are. In your answer book, copy and complete the truth table for the system showing. Right. So if you were looking at your notes, a NAND gate is a combination of an AND gate followed by a NOT gate. The output of a NAND gate is 0 only when both inputs are 1. Okay, so these are the inputs over here, A, B, C. When these inputs, when both of them are 1, you get a 0 over here at D. So for example, we'll just go through the first one here. So if A is 1 and B is 1, then D is 0. Okay? So when A is 1, when B is 1, D is 0. And if D is 0, then the motor doesn't turn on. Okay? Hopefully that makes sense. Now, when is A and B 0? Right? When the inputs are 1, they're in darkness. Okay? So when there is no light being detected at A and B, there are two inputs of 1. The NAND gate flips that around and gives you out a 0, not turning on the motor. However, if I was to say that B is still at 1 and C now, someone points a laser or something over here or turns on a light over here, and since this is 0 because there's light over here, there's a 1 here, therefore there's a 1 there. 0 and 1 will give the NAND gate will flip that around and will give us a 1. Therefore, motor 2 turns on. Okay? So, if we were to use that logic, and I think we should, when A and B are together, both 1s, we get a 0. When B and C are together, we get a 0. When A and B are together with 1, we get a 0. When B and C, when B is 1 and 0 and C is 0, we get a 1. For all other combinations in an AND gate, they all get 1s, so the motor is turned on for all other combinations. Okay? So, I'll repeat there again. The output of the NAND gate is 0 only when both inputs are 1. So most of the time, the output of an AND gate is 1. Most of the time. Okay, you've 4 chances, and 3 out of those 4 are going to be 1. Okay, the only time it's 0 is when both of the inputs are 1. Okay. Question 2. From the truth table, identify the sensor states, either light or dark, which will cause the buggy to turn left or turn right. Okay, we want to get something turning. We want one of the motors to be turned on. Okay? So how are we going to get that motor to turn on? Well, one of them has to be 1 anyway. If you wanted to get it to turn in one direction, they can't be both turned on. So only one of the motors can be turned on at this stage. So we go over to our truth table. We see, is there any state that only one motor is turned on? If I go over here, I can circle this one here. That's E. That's the motor 2 turned on there. D is not turned on. In everyone else, they're all turned on. Okay, so this is the line I'm looking for. So what I'm saying is A and B are both 1s with C as a 0. So we can write that as A plus B equals 1 and C equals 0, or we can write it in words A plus B equals dark. So both A and B are dark and C is in the light, right? The opposite can be said as well if you were to flip it around. Okay. The part C, so right, this is the one that might catch someone. Everything else can be kind of learned off, I suppose, or worked out logically. This is the part where you have to really use your knowledge of logic gates, and don't worry, you'll get that too. Okay, so I'm going to read out the question. Outline a suitable modification to this system which will turn on a flashing LED. Now, it doesn't really make a difference if it's flashing or not, right? You don't need to have some special, you just call it a flashing LED or just write LED or whatever. Only when both motors are turned off. Now, that's important that both motors are turned off. So, if we go back up here, we can see, we'll have to see that this has to be 0 here and this has to be 0 here for both motors to be turned off. Now, I'm just going to, I put a few bits of information down here. NOT gate, right? is a NOT gate reverses the input, so when the input is 1, the output is 0, right? So it switches it around. That's the symbol for it, the triangle with the 0, or with the circle at the end of it. An AND gate is both inputs need to be 1 to get Y, so the output equal to a 1. That's the symbol again. So both of these need to be 1 to get a 1. Right? If either of those is 0, so if you have 1 and 1, you get 1. If you have 1 and 0, you get 0. If you have 0 and 1, you get 0. If you have 0 and 0, you get 0. So if I was to take this one first and then add this chap onto the end of it, right? No matter what you get, except for obviously a 0 coming out of this fella, you'll turn this LED on, right? So if I was to look at this scenario here, I put 2 NOT gates here attached to both D and E. So before the motors, or attached onto the motor, I have a NOT gate coming out the side, right? Coming out of each output. If D is 0, right? If D is 0, the NOT gate is going to be 1. If E is 0, the NOT gate coming out of that is going to be 1. Now if I have an AND gate here, I told you up here both inputs need to be 1 to get Y equal to 1. So if both of these are 1, we'll throw a 1 in there, a 1 in there, 1 plus 1, and turns out to be 1. That lights my LED. Okay, I know this is a little confusing. I suppose it's somewhat new to some fellas. Hopefully, if you look at that question and look at those notes that I've sent you, we'll be able to figure that out together. Okay, if you have any questions, don't hesitate to contact me.